Hi everyone, it's Professor Pemberton. In this video we're going to talk about transformations of functions. So in this section we're going to study how certain transformations of a function actually affects its graph. This will give us a better understanding of how to graph a variety of different types of functions, and the transformations that we're going to talk about are shifting, reflecting, and stretching. So in this video we're going to talk about how to graph functions using vertical and horizontal shifts, and also how to graph functions using reflections about the x-axis, y-axis, or origin. Vertical shifting. One of the simplest kind of transformations about a graph is actually shifting the graph up or down. And so if you add a constant to the function, it will shift the graph up vertically if the constant is positive, and it'll shift the graph down vertically if the constant is negative. So suppose that we have a constant, a real number c, that's greater than 0. If you want to graph the function y equals f of x plus c, so you know what the graph of f of x will be. It'll be some basic type of function's graph. If you add c to that function's graph, that will actually shift the graph upward c units. And if you want to graph the function y equals f of x subtract c, then you take the function y equals f of x and you shift it downward c units. So these graphs will give you an idea of what happens when you actually shift the graph upward or downward c units. So if you take y equals f of x, that will be some function's graph originally, so that's one that's in blue. And if you want to graph the y equals f of x plus c, that would be a vertical shift up c units. You take every single point on the graph of y equals f of x and you add c. That means that you would be adding c to the y values. And so the same x value, but the y value will add c, which is exactly what this means. F of x plus c means take the y value at x and then you add c. And so every single point will be shifted up c units. On the other hand, if you're subtracting c, you start with the graph y equals f of x, and if you're subtracting c to all the y values, that will shift the graph downward c units for every single point on the graph of y equals f of x. And so this is a simple transformation. It's called vertical shifting, up or down. So let's take a look at example 1. Example 1, vertical shifts of graphs. Starting with the graph of the basic function, describe the transformations used to obtain the graph of f of x, then graph the function. So number 1, we're going to graph the function g of x is equal to x squared subtract 3. Now you could graph this by plotting points, but we're going to understand what does the graph actually look like with a vertical shift up or down. In this case, it looks like the basic function is like y equals x squared. So that would be the parabola, y equals x squared. It passes through the origin at 0, 0. It also passes through the point at 1, 1, and also at negative 1, 1. Now, if you want to graph g of x, notice that you're taking y equals x squared and you're subtracting 3 to the entire function. That's going to be a vertical shift downward 3 units. So the entire graph will be shifted down 3 units. So every single point, 0, 0 will be shifted down 3 units, so that point will now be at 0, negative 3. 1, 1 will be shifted down 3 units, so that will be at 1, negative 2. And negative 1, 1 was on the graph of y equals x squared. If that's shifted down 3 units, you'll be at negative 1, negative 2. And so if you have those 3 points identified, you have an idea of what the graph will look like for y equals x squared subtract 3. It's the entire graph, but shifted down 3 units. So a vertical shift down 3 units would be the transformation. And this is what the graph will look like for g of x. Okay, number 2, h of x is equal to square root of x plus 4. It looks like this time the basic function is y equals square root of x. And so that would be the graph that starts at 0, 0, and also passes through 1, 1, because the square root of 1 is 1. And it will also pass through 4, 2, because the square root of 4 is 2. And so notice that you cannot plug in negative values into the square root function because you'll have imaginary numbers or complex numbers. Those don't exist as real numbers. And so now if you want to graph h of x, identify what the transformation is first. It looks like you're starting out with y equals square root of x, and then if you want to graph h of x, you would have to shift the entire graph up 4 units. So the transformation is a vertical shift up 4 units, and that will affect every single point on the graph of y equals square root of x. So at 0, 0, that will be shifted up 4 units, so the graph will start at 0, 4 now instead. 1, 1 is shifted up 4 units, so that will be at 1, 5 now. And 4, 2 will be shifted up 4 units, and that will be at 4, 6. And so this will give you an idea what the graph of h of x looks like when you have the square root of x, and then you shift the graph up 4 units to get square root of x plus 4. Number 3, let's graph the function k of x is equal to the absolute value of x, and then subtract 2 outside the absolute value. So it looks like the function that we're going to start off with, the basic function's graph will be y equals absolute value of x. So if you start with y equals absolute value of x, it looks like the subtract 2 is outside the absolute value, so that means that the entire graph will be shifted down 2 units. So the absolute value function graph, we know that there's a vertex at 0, 0. The graph will have a slope of 1 on the right side of x equals 0, and so it'll pass through 1, 1, 2, 2, and so on. But then whenever x is negative, the graph is y equals negative x. And so the graph will pass through negative 1, 1, negative 2, 2, and so on. If you shift the entire graph down 2 units, the vertex is now going to be at 0, negative 2 for the graph of k of x. 1, 1 shifted down 2 units makes it 1, negative 1 is the point on the graph of k of x. And then negative 1, 1 shifted down 2 would be at negative 1, negative 1. And so the graph will have the same shape. It'll still be a V-shaped graph, but the graph will pass through 0, negative 2, 1, negative 1, and so on. And it will also pass through negative 1, negative 1 whenever x is negative. And so this is a vertical shift down 2 units to get the graph of k of x. So now there's a different type of transformation that we're going to talk about that involves shifting the graph left or right. And this is called horizontal shifting. Suppose that you have the graph y equals f of x, so a basic functions graph again. How do you use it to obtain the graphs of y equals f of x plus c and y equals f of x minus c? So notice that you have x plus c inside the function notation. So that means you're replacing all the x values with x plus c to obtain this function's graph, and you're taking all the x values and replacing with x minus c to get the function's graph of f of x minus c. What does the c do if c is a positive number? Well, if you're trying to find out the value of f of x minus c at x, notice it's the same y value at f of x whenever x is equal to c. Since x minus c is c units to the left of x, then the graph of y equals f of x minus c is just the graph of the y equals f of x function, but it's actually shifted to the right c units. So notice if you have a minus c inside the parentheses for the function, it's actually going to shift the graph c units to the right. And then using similar reasoning, if you want to graph the function y equals f of x plus c, then you start with the graph of y equals f of x, but the graph will be shifted to the left c units because there's a plus c on the inside of the parentheses. You'll actually shift it to the left c units. And so now identifying what will happen with the graphs, let's say you start with the graph of y equals f of x, that's this graph that's in blue again. If you want to graph y equals f of x minus c, notice that the minus c will actually shift the graph to the right c units. And so every single x value will be increased by c. The y values will stay the same, but the x values will increase by c when you shift it to the right c units. And that's called a horizontal shift right c units. If you want to graph the function y equals f of x plus c, then you start with the graph of y equals f of x, the one that's in blue again, but you shift the graph c units to the left. And so all the x values will be subtract c to get the graph of y equals f of x plus c. The y values stay the same, but the x values have to be shifted to the left, c units. And so this is called a horizontal shift left c units. So example 2, horizontal shifts of graphs. Start with the graph of the basic function. Again, describe the transformations used to obtain the graph of f of x, then graph the function. So number 1, we're going to graph the function g of x is equal to parentheses, x subtract 2 inside the parentheses, and then the whole function is being cubed. So notice that instead of an x, you have inside the parentheses, you have an x minus 2. So it looks like you're actually shifting the graph to the right this time because there's actually a subtract 2 inside the parentheses. But let's identify the basic function first. It looks like instead of an x cubed, it's x subtract 2 cubed. So we're going to start with y equals x cubed. That would be this graph. The graph passes through the origin at 0, 0. It'll pass through 1, 1 because 1 cubed is still 1. And it'll also pass through the point negative 1, negative 1 because negative 1 cubed is also negative 1. And so if you want to graph the function g of x equals the parentheses x subtract 2 all cubed, there's a subtract 2 inside the parentheses, so that means that you're shifting the entire graph to the right 2 units. So that would be a horizontal shift right 2 units to be the transformation. And so all the x values are affected. You need to add 2 to the x value, but the y value stays the same. So instead of 0, 0, now that point will be at 2, 0. Instead of 1, 1, that point is now at 3, 1. We're adding 2 to the x values each time, but the y values stay the same. Negative 1, you add 2 to the x coordinate, and that would be 1, negative 1. And so you get the graph that is dashed would be y equals parentheses x subtract 2, and then the parentheses is being cubed. That would be the function's graph. It would be based on a horizontal shift right 2 units. So number 2. We're going to graph the function h of x is equal to the cube root of x plus 8. Notice that the plus 8 is inside the cube root. So again, it looks like the basic function that we're going to start off with is y equals the cube root of x. It looks like we're adding 8 inside the cube root with the x. And so instead of an x inside the cube root, it's an x plus 8. So if there's a plus 8 inside the cube root, we've added 8 to the x coordinates. So that means we're actually shifting the graph to the left 8 units. So this is what the graph of y equals the cube root of x looks like. It passes through 0, 0, 1, 1, because the cube root of 1 is 1. The cube root of -1 is -1, so it also passes through -1, -1. And so the graph will continue going up in this direction as you go from left to right. And so if you add 8 inside the cube root with x, then you're replacing the x with an x plus 8. That means you're shifting the entire graph to the left 8 units. Instead of 0, 0, that will be at -8, 0 now. 1, 1 will now be at -7, 1. And -1 will now be at -9, -1. You're taking all the x coordinates and you're subtracting 8 to get the point on the graph of y equals the cube root of x plus 8. But the y values stay the same. And so if you want to get the graph of y equals the cube root of x plus 8, where plus 8 is inside the cube root, it's a horizontal shift left 8 units. And number 3, let's graph the function k of x is equal to the absolute value of x plus 4, but this time you have plus 4 inside the absolute value, whereas the last example we had a subtract 2 outside the absolute value. So there is a difference between the transformations between the last example and this example. It looks like we're starting with the absolute value graph, so let's start with y equals absolute value of x. If you want to graph the function k of x, absolute value of x plus 4, where x plus 4 is inside the absolute value, you need to shift the entire graph to the left 4 units because it's a plus 4 inside the absolute value. So instead of an x inside the absolute value, it's x plus 4. That's a shift left 4 units. So let's start with the graph of the absolute value of x first. So you have the vertex at 0, 0. It passes through 1, 1, 2, 2, and so on. It also passes through -1, 1, -2, 2, and so on. So it's a V-shaped graph for the absolute value of x. If you want to shift the entire graph to the left 4 units, that would be a horizontal shift left 4 units. It's the transformation. 0, 0 is the vertex. Now the vertex will be at -4, 0 because you subtract 4 from the x values, but the y values stay the same. 1, 1 becomes -3, 1, subtract 4 from the x coordinate, and -1, 1 becomes -5, 1 on the graph of y equals absolute value of x plus 4. So you'll still get a V-shaped graph, but the graph has been shifted to the left 4 units for every single point on the graph of y equals absolute value of x. Alright, so those are vertical shifts up or down, or horizontal shifts left or right. Now we're going to talk about one more type of transformation in this video called reflections. So we're going to reflect graphs. Suppose that we know that the graph of y equals f of x looks like. How do you use that graph to obtain the graphs of y equals negative f of x and y equals f of negative x? So let's start by talking about this graph, y equals negative f of x. Notice that the y coordinate for each point on the graph of y equals negative f of x is the opposite sign of the y coordinate of the corresponding graph of y equals f of x. So instead of y equals f of x, notice that we're only introducing the negative sign in front of f of x. Well, f of x stands for the y values. So if you're introducing a negative, that will change all the y coordinate sign. So instead of a positive y coordinate, it'll actually be a negative y coordinate. Instead of a negative y coordinate, you'll have a positive y coordinate. And so if you do that for every single point on the graph of y equals f of x, you actually get this graph, y equals negative f of x. It's called a reflection of the graph of y equals f of x across the x-axis. On the other hand, if you want to graph y equals f of negative x, where the x is being replaced with the negative x inside the parentheses, the y values at x is the same as the y value at negative x, or y equals f of x. This means that the graph of y equals f of negative x is going to be a reflection of the graph of y equals f of x across the y-axis. So the y values stay the same when you change x to negative x. If you do that for every single point on the graph of y equals f of x, you actually get the graph of y equals f of negative x, and that's a reflection across the y-axis. So let's talk about what happens to the graph when you're talking about reflections of a function's graph. So let's talk about reflection across the x-axis first. So we start off with y equals f of x, the one that's in blue again. If you take all the y coordinates on the points of the graph of y equals f of x and you change the sign, so this point, if you change the sign of the y coordinate, will now be down here. It'll be a negative y value. If you do that for every single point on the graph of y equals f of x, you get the graph of y equals negative f of x, where all the y values have been changed sign. And so you notice that the graph is actually a reflection across the x-axis. On the other hand, if you start with y equals f of x, the graph that's in blue here, if you change all the x values to negative x and you still get the same y value, so you change all the f of x to be f of negative x, so the x values are changed sign, but the y values stay the same, then you get a reflection across the y-axis. So this point, if you reflect across the y-axis, you'll have this point on the other graph of its reflection. And if you do that for every single point, you'll get the graph of y equals f of negative x. And that's a reflection across the y-axis. So let's finish up with example 3. Example 3, we're going to reflect graphs, starting with the graph of the basic function, describe the transformations used to obtain the graph of f of x, then graph the function. So number 1, the function is g of x equals negative on the outside of the parentheses, then you have x plus 3 on the inside of the parentheses, and the parentheses is being squared. So if you want to find out what the graph of this function g of x looks like, it looks like we're going to start off with the basic function y equals x squared. So start with the parabola, y equals x squared. The vertex of the parabola is at 0, 0. Y equals x squared will pass through 1, 1, and also negative 1, 1. Let's identify what the transformations are to actually obtain the graph of g of x. Notice that instead of an x, you have an x plus 3. We talked about in the previous example that the plus 3 inside the parentheses with the x will actually shift the graph horizontally left 3 units. So that's one transformation. But then also notice that there's a negative on the outside of the parentheses. This is not replacing x with negative x, it's replacing the entire function x plus 3 squared with a negative x plus 3 all squared. So it's going to change all the y values from positive to negative or vice versa. So this is a reflection across the x-axis. And so let's see what happens to these 3 points on the parabola y equals x squared. Instead of 0, 0, we're going to shift the graph left 3 units, so it'll be at negative 3, 0, and now reflect across the x-axis. Well, that point is on the x-axis, so it stays the same. Because y equals 0, if you change the sign of y equals 0, you still get y equals 0. So that point is at negative 3, 0, that's the vertex of the parabola for g of x. At 1, 1, let's shift the graph to the left 3 units. That would be at negative 2, 1. And now reflect the graph across the x-axis. You'll get negative 2, negative 1 when you change the y-coordinate from positive 1 to negative 1. So that point 1, 1 is now at negative 2, negative 1 on the graph of g of x. And now negative 1, 1, let's shift the graph to the left 3 units. That would be at negative 4, positive 1. And now reflected across the x-axis, that point will be at negative 4, negative 1 now. And so now you have these 3 points to give you an idea what the graph will look like. The parabola will open down instead, and it'll pass through negative 3, 0, negative 2, negative 1, and also negative 4, negative 1. That is the graph of g of x is equal to negative, and then parentheses x plus 3 inside the parentheses, and it's all squared. That's a horizontal shift left 3 units, and a reflection across the x-axis to obtain the graph of g of x. And then number 2, if we want to graph the function h of x is equal to square root of negative x inside the square root, and then subtract 4 outside the square root. It looks like we're going to start off with the square root function. So start off with y equals square root of x. So that would be a graph that starts at 0, 0. It will pass through 1, 1, because the square root of 1 is 1, and it will also pass through 4, 2, because the square root of 4 is 2. So that's the graph of y equals square root of x. Again, notice that the domain for this function is 0 to infinity, only positive values for x, or is equal to 0. So if you want to graph h of x, let's talk about the transformations to obtain that graph. So you start off with y equals square root of x. Instead of an x inside the square root, you have a negative x. So we talked about that's a reflection across the y-axis. And then you have a subtract 4 outside the square root. That is a vertical shift down 4 units. So the transformations are vertical shift down 4 units, but also a reflection across the y-axis. So let's see what happens with these 3 points when we look at the graph of y equals square root of x, and then we want to obtain the graph of h of x. 0, 0, we want to shift the graph down 4 units, so that will now be at 0, negative 4, and now reflect across the y-axis. That point is on the y-axis, so it stays the same. The x-coordinate is x equals 0. If you change the sign of the x-coordinate, it still is 0. So that would be at 0, negative 4. 1, 1, if you shift the graph down 4 units, that would be at 1, negative 3. And now you reflect it across the y-axis. That becomes negative 1, negative 3. So notice that the x-coordinate changed sign from positive 1 to negative 1, and the y-coordinate stays negative 3. And then 4, 2, if you shift the graph down 4 units, that would be 4, negative 2, and now reflect across the y-axis, you'll get negative 4, negative 2. And so again, the x-coordinate changes sign over reflection across the y-axis, from positive 4 to negative 4, but the y-coordinate stays negative 2. And with these 3 points graphed, you get the idea what the graph of h of x will look like. The graph will start at 0, negative 4. The graph will go up as you go to the left, passing through negative 1, negative 3, and also negative 4, negative 2. And so again, this is a reflection across the y-axis, and also a vertical shift down 4 units to obtain the graph of h of x, square root of negative x, and then subtract 4 outside the square roots when you start with y equals square root of x. So this is a good place to stop our video now that we talked about vertical shifts up and down, horizontal shifts left and right, and also reflecting graphs. If you have any questions about any examples of this video, please let me know. Or if you have any questions while you work on the homework for this section, please let me know that as well. And I'll see you at the next video when we talk about vertical stretching and shrinking, horizontal stretching and shrinking, and also even and odd functions.